Hello everyone. We're going to be going over the very first Pivot Interactive lab called Ping Pong Ball Bazooka. So here we go. So here is the lab. Intro to Motion Graphs, Ping Pong Ball Bazooka. It's out of 20 points. That might change by the time you guys actually see the assignment, but that's what I have in here so far. Learning objectives: describe the motion using a graph and describe the motion mathematically. And I need to add one in there basically saying just figure out how the heck to start using these Pivot Interactives. So let's go ahead and get started. The first piece is right here. You'll see a video in this. If we just hit play, boom, that's a ping pong ball in a vacuum cannon destroying a can. And what's cool is these, if you click the link, it'll give you some info, but these will actually break the sound barrier. And we want to try to use all of the tools and graphical analyzing tools and everything we have in Pivot Interactives to basically model the motion of this thing graphically and mathematically. All right, so first it says let's try making some measurements from the video. So to control the video, you can use the screen controls. So up here is where you'll get to the tools. And right here is where you have all of the screen, like the video control options. So I can go forward a frame by just clicking. So right now I'm actually progressing the video just by clicking. Right? I can go and you can see click. I'm going forward a frame at a time. If you ever want to skip back to the beginning, you just hit the little reset button. Right? If I wanted to, I could do this with the keyboard as well. I hit space to stop it, or I can hit the right key or the left key to go forward and back. All right. And then the tools. So this says, first question, use the ruler tool to measure the distance from the right edge of the ball to the left edge of the soda can. So I want to get this thing to where the ball just came out of the cannon, right there. Okay, and so to get the ruler, I'm going to go up and click my tools icon and get the ruler. And I'm going to place that zero line of the ruler right at the front, the right side edge of the ball. And let's just make it easier on ourselves. Let's put it right there. Okay. And so it's zero right there at the front of the ball, and over at the soda can that looks to be about 52 centimeters, right? There's the big 50. Oh, undo doesn't work. All right, 51, 52. So we'll select about 52, submit, and it gives me great work, which means it was right. Okay, so moving on. Now we're going to use the stopwatch to measure time. We're going to hit the stopwatch looking button. Okay. And notice right here, this is from the very beginning, right? It thinks that the very beginning is time 0, frame 0. And as this goes on, let's get that ball shooting out. It's saying that this is the 43rd frame of the video and 0.016 seconds have passed. We want this to be time 0. So I'm going to click this little reset time button right there. And now it's there where this is 0 and 0 seconds have passed and 0 frames have gone by. This is effectively our new 0 time. Okay. And I want to figure out how long does it take for the ball to move from the muzzle of the ping pong ball bazooka to the pop can. So there's 0. I'm just going to go forward frame at a time until it hits the can. Right around there. So that's 0.00269 seconds. So which one of those? Right there. C. Submit. Hey, great work. I know it's right. Okay. So moving on to the second part, graphing directions. This whole thing, this whole section is, it's a good section. You definitely want to read through it, but it's just explaining all of the things we can do when making a data table. Okay, so I'm actually just going to go and make the data table now. In this section, you'll record some data. and make a graph from our data. All right, so there's a data table that's already set up, but notice it doesn't have any values in it, any values, any names, anything. So we are measuring the two variables of position and time, right? So my first column is going to be time. Units for time would be seconds, so SEC for seconds, or S for seconds. Variable for time is a lowercase t, so I'm going to put that in there. And then the other column we're measuring is position. Units would be centimeters. Variable, x. We always use lowercase x for horizontal position, okay? And so here's my video with my tools. So I want to get this to right where it comes out of the bazooka. Remember, just like last time, I want to make that 0, okay? And the hard thing is we could do this, and you could just progress. So at 0 seconds, it has a position of 0, okay? I can then scoot it forward. Whoop, shoot, didn't mean to do that. I meant to put the stopwatch up there. And I'm going to reset it so it's at 0 seconds. All right. So now I'm going to go forward to 0.00038 seconds. And I'm going to see that it has a position of, and last time, that 0 was at the right side edge of the ball. So I'm always going to measure on the same spot. So I'm always going to measure at the right side edge of the ball. So when I go forward, okay, the right side edge of the ball is at 5, 6, 7, right around 8 centimeters. So we're going to say 8 centimeters. All right, next one, that's a time of 0.00077 and has a position of 15, almost 16. We'll round a little bit. All right, it's kind of between there, so you could say 15.5 if we wanted. All right, next frame, 0.0015, and has a position of 21, 22, 23 and a half. Okay, and I'm going to fill in the rest of these in following that exact same process. To get another, what's that, a row? To get another row to show up, all I did was at the very end of this one, I just hit enter, and it made another row for me. Okay, so I've gone through and measured all of the positions and times for the ping pong ball as it's going to the can. And the cool thing is, I don't know if you noticed, but as you are putting these points into the data table, it's actually mapping this out for you in the graph. So something's not happy between these two, 0.0015 and 154. So I probably copied something down wrong. 0.00154. 0.00115. 115. There we go. That looks like a nice pretty line. Okay. So just double check. You know, we as physicists normally put time on the horizontal axis. So time should be down here. If your time is not there, all you have to do is click where that variable is, and you can switch which one of the columns from your data table you want there. Okay. So I want time on the horizontal axis. I want position in centimeters on the vertical axis. And that seems to be what we need. And then I can click this settings button right here to start figuring out some curve fits. Okay, so I want to get a line of best fit for this data. And so if I go curve fits, well, that is a linear, that looks pretty darn linear to me, right? Straight line, if I drew a straight line, that would fit that data very well. So curve fit, linear fit. And there we have our linear fit. And it gives the variables and everything as we have. So position x is equal to some constant, that's the slope, a, times the horizontal variable, time t, plus whatever the intercept is. Now what the heck is that? 2.03 e plus 0.4. Boom. All right. Now I'm figuring out this as well with you. So how do I get it to score my stuff? I think this might have to come from me grading your stuff. Okay, but we'll see. Interpreting your graph. In this section, you will use your graph to figure out the key concepts. So take a look at the box below. So in this, it has y and x. We used position x and time t. So describe the shape of your graph. The graph is linear. And the line of best fit goes through, or nearly through, all points. Okay, we are now going to focus on the motion of the ping pong ball before it collided with the can. First, review the video and find the time the ping pong ball hit the can. Well, I stopped right around when the ping pong ball hit the can. So it's right around, what is that, 0.00269 seconds. Okay, so if I wanted to ignore some points, I could click on a point and everything behind it. Oh, if I click on a point, it takes it out of the data table. Cool. So you can see, like, if I take this data point out, watch down here. If I take the data point out by clicking it, yeah, it changes the numbers a little bit, because now it's calculating the line of best fit with some slightly different data points. So yeah, if you click a point, you can take out the data point. Cool. Describe the shape of the line of best fit. Yup. Still linear. And goes through all the points. A represents the slope of your line of best fit. So A is a constant. Pay attention to the number on this unit. Oh, 2.03 e to the fourth. So that's because it's it's going up so high, because this is basically saying 8 over 0.0005. Yeah. Let's see. If you have an E in your number similar to the screenshot, check the formula used to get the position in meters. So do we only want meters then? So let's change this to meters and see what happens. 0. That's a centimeter is 100, or sorry, there are 100 centimeters in a meter. So we just need to move the decimal place to the left 2 times every time. All right, there we go. Looks a little nicer. 203 meters per second. Okay. find your slope. What is the slope of our line? 203 meters per second. Okay, turn your slope into a for every statement. Every second, the ping pong ball travels 203 meters. Okay, if I was someone that fully read the directions that I even wrote a while ago, right? The quantity on the vertical axis, the position goes up 203 meters for every 1 second of time. That is technically, if you're just filling in the blanks right there, that is exactly what it would look like. Or the first one, which says the same thing. Either one of those would work. Okay, B right there, the B constant represents the intercept of our line. That would mean, where is this line intercepting the position axis? Okay, so our intercept was 0.000758. So let's see, 0.000758 meters, because it's intercepting the position axis. Turn your intercept into a statement. The position is 0.000758 meters when the time is 0. What does that mean? That means by our, oh, here we go. Does our intercept make sense? Yeah. The ping pong ball should be at position 0 when the time is 0. Our math model basically is saying that really well. Okay, and write out the equation for your line of best fits. So remember, line of best fit is normally y equals mx plus b, correct? Well, our y, our vertical axis, you know what? You know what we can do? Oh my gosh. I'm going to, you can skip ahead a few seconds until I get this set up, but I got my handy dandy little drawing thing here. All right, so this is our little setup for how we're going to make our math model, and just a couple things that we do know. We know that the slope is 203 meters per second, and we know the intercept is this crazy small number. And just so remember, this was a line, the graph, so this is, we're making an equation of a line, and it's a model for that line, so we want to have the correct units and numbers that represent our data, okay? So y equals mx plus b is our typical equation to represent a line. The y stands for the vertical axis of your graph. The x right there stands for the horizontal axis of your graph. So in our graph and data table, what we had was a vertical axis of position. So I know it's kind of confusing, but x for us in this case represents horizontal position. Equals, and then we had whatever our slope was. We'll put that in here in a sec. The horizontal axis right there, in this case for our graph, was time. So I'm going to put a lowercase t for time. Plus, and then we have a space there at the end for whatever our intercept was. Okay, so now let's put in our numbers and units that represent our data. So the slope was 203 meters per second. And then the intercept was 0.000758 meters. All right. And that right there, ladies and gentlemen, is a math model. Let's get yellow. That's a math model for our data right there. Cool. An object's change in position for every 1 second of time is defined as its velocity. The velocity will also be the slope of the object's position versus time graph. Well, if that's the case, then I need to go a few more data points up here after it hits the can. So let's see. Boom, boom, boom. Now let's see where it's at. I need to reset my little ruler. Okay. Boom, 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 boom. Boom. So this would be at 0.00308. It's at position 61, it looks like. And then at 0.00346, it's at position 66. We'll do a couple more. 0.00385, it's at position 71. And last one. 0.00423, it's at position 76. Whoop, 6. Okay, see how those points really screw up our data? So if I say, hey, I want to ignore those, I'm going to click each point. Okay. Oh, that's why. I did that thing again. Point, 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 point. Boom. Right, see there's after. Right, so both of them look like lines. This would be a straight line going to there. And then if I was to take out all of those other points, that looks like a relatively straight line that fits those data points after it hits the can, right? So each one could have its own line that represents it. And since the slope, here's where we start getting into the nitty gritty. That was the 0.5, last one. Okay. If the slope represents the velocity, right? That means that this velocity, the slope is the same throughout an entire line, so the velocity is staying the same, right? As soon as it hits the can and then there's a new line, that means there's a new constant velocity after it hit the can. Okay, so when we go down and answer our question, we'll make our claim, provide a little bit of evidence, and explain how the evidence to answer this question. How does ping pong ball's velocity before it collided? The velocity of the ping pong ball was greater than the velocity ping pong ball before the collision the slope before the collision is steeper than the slope after the collision. This means the magnitude of the velocity before the collision is steeper than after. Boom. Okay. So a bunch of stuff, but hopefully we were able to walk through it a little bit. I'm playing around with some new screen recording software, so this could be a good video or it could be awful. We'll see. But I'll catch you guys later. Now I got to figure out how to turn it off.